Welcome back. We're going to switch gears now and talk about the Z-transform. We'll eventually bring all of this together that we've talked about, but we need a few more tools under our belt. Now, in the prerequisites for this course, you've been exposed to the Z-transform before, so we'll go a little bit quickly, but we'll still give you enough that if you don't remember, we should be able to bring things back for you. Okay, so the Z-transform is very closely related to our DTFT. However, as we've seen, there are many times when the DTFT has convergence problems. The unit step, a cosine, and random signals are all examples when this has problems converging. So, the Z-transform is partially developed as a way around that. It turns out there are many applications of the Z-transform, including in combinatorics and other disciplines where you might not expect the Z-transform to be very useful, but it does in fact prove useful. The Z-transform is defined in essentially the same way as the DTFT, except that instead of e to the negative j omega n, we will just put z to the minus n. So that's the definition. The inverse Z-transform, like the DTFT, involves an integral. But this integral is a little bit different, and it actually comes from complex analysis. It's a contour integral that encloses every pole or every critical point within the Z-transform itself. We won't be doing this integral. In fact, for some types of problems, this may come up. But in signal processing, we instead, actually, maybe I should explain this differently. Instead, in signal processing, we will pretty much do the forward transform, build a table of those, kind of like laying down breadcrumbs so we know which way to get back. We'll go find the transforms in the table and go backwards. Since we're always dealing with rational Z-transforms, this works for us. And in fact, the contour integral really comes down to the same basic process in practice. So, there we go. Well, we brought this up because of convergence. So, what about convergence? I will say here that the textbook that we use spends quite a bit of time discussing the convergence of the Z-transform. I've spoken with other professors here at Georgia Tech in DSP, and we tend to agree that some of the issues on convergence are actually very important in one case or one condition, and that is passing exams and doing homework in 4270. And that since they took the equivalent of this course, they have never ever again worried about the convergence of the Z-transform when dealing with real problems. So, what does that mean? That means that we're going to play down and not spend a lot of time on the convergence aspects of the Z-transform. We're going to spend just enough so you know what's going on, and then we'll move on to actual applications of the Z-transform. Okay, so for convergence, we need this to be finite. And that's what it comes down to. And by definition, we get this second term. And by the triangle inequality applies to three things, and we have an infinite number of things. This is a really big triangle, but still, the triangle inequality holds that the absolute value of a sum of things is less than or equal to the sum of the absolute values. And then we go one step further and we say if we have two complex things, then the absolute value of the product is equal to the product of the absolute values. So that brings us to, gives us this bound, this inequality. So the region of convergence, you will see this in the reading, and we will spend just a little bit of time, as I've talked about, on it. The region of convergence is the set of values of Z such that original sum converges to something finite. Okay, let's look at an example. We want to know the region where in the set of values such that Z converges. So we'll start with the example of x of n is equal to a to the n times u of n. The Z transform is pretty straightforward. X of Z is equal to the sum. Because of the u, we can just start at 0 and go to infinity of a to the n raised to the power of n, Z raised to the negative n, which is just the sum from n equals 0 to infinity of a Z to the minus 1 raised to the n. So we have a formula that can take care of that. I'm going to do just a quick aside, and I sometimes can't remember it. It doesn't stick in my mind, but I remember how to derive it, and it takes seconds. So let's assume that we have some sum of powers up to alpha capital M. Then if we write alpha S, we get a power, sum of powers now up to alpha m plus 1. Most of these terms are in S. So this is equal to S plus alpha to the m plus 1, because that's a new term. And S also includes alpha 0, so we need to subtract it off. Okay, now we can solve for S. S is equal to alpha to the 0, which is just 1. So let's put that, minus alpha m plus 1, all over 1 minus alpha. So we made no assumptions about what alpha was or anything. It just holds in general. So now back to here, we'll have alpha be our a times z to the minus 1. And so this is going to be just equal to 1 over 1 minus a z to the negative 1. Well, what happened to the second term, alpha to the m plus infinity? That is, if a z to the minus 1 is less than 1, then raising that to the power of infinity would be 0, and we would be just left with this. So maybe I shouldn't have put that in gray, maybe it should be in red. Very important finding. Okay, in fact, this is what many regard as kind of the building block of your traditional Z transform of different data. You have this Anytime you have a signal that's raised to a power, you end up getting something like that. Okay, so back to this term. When is this true? Az to the minus 1 less than 1. Well, it's when, another way to write that is as A over Z. And we leave it in terms of Z to the minus 1 usually for reasons that I think become apparent as we move along. But that has to be less than 1. In other words, Z has to be greater than A in magnitude. When Z is larger than A. So we see this drawn like so. Okay, even when I'm using the drawing tools, I can't make a perfect circle plot, but I'm not going to spend any more time with it there. So that's 1, that's J, so this is the imaginary plane. We have the real axis and the imaginary axis. And this would be then the unit circle. And the unit circle is basically defines that, and in fact for any omega ranging over 2 pi, we get the unit circle. So if A, let's assume that A is right here, the magnitude of Z has to be greater than the magnitude of A. So everything, I did a dashed line because it's greater, not greater than or equal to. So everything outside here is the region of convergence. So in general, we want the region of convergence to include the unit circle. It is possible, for example, to choose maybe A is 7, and so we choose Z to be 8, or at least anything larger than 7, and the sum will converge. But that's it's only academically useful at that point, because really what we would like to do after we are done playing with our Z transforms, we would like to eventually come back to the point where we can make this substitution, which is if we take x of Z and we substitute Z is equal to e to the e to the j omega, the negative is already taken care of, then that's equal to x e j omega. And now you're seeing why we use this notation, which is just the dt ft. where we had z to the negative 1, we now have e to the j omega to the negative n, giving us our dTft.